Dr. Vinod, you are not audible.
Okay, yes. Good evening to all the participants connected with us on this knowledge platform virtually, and I welcome back to the last talk of this 5-day schedule of ESTC on current trends on condensed matter physics. It's a great pleasure to welcome Dr. Sanjeev Kumar. He is currently an associate professor at Indian Institute of Science, Education and Research, Mohali. Welcome, sir. A physicist whose reputation precedes his work. Thank you, sir, for willingly accepting our invitation for being here with us today on this virtual platform. So your presence here is truly momentous and significant for all of us, and it will be very encouraging for all the participants. Uh, Dr. Sanjeev obtained his BSc from DAB College, Kangra, HPU Shimla, and MSc from IIT Kanpur, and PhD from HRI Allahabad. He worked as a postdoctoral fellow at University of Augsburg, Germany, from 2004 to 2007, University of Eichstätt, Institute Lawrence, Leiden University from 2007 to 2009, Institute for Solid State and Material Research, Dresden, Germany from 2010 to December 2010. So with 48 refereed journal publication, one each in Nature, Scientific Report, and 18 in Physical Review Letter, and mostly all papers in PRV. Okay, so he is such a caliber person in this field, and about his research interest, it caters to research what he focuses on studies of electronic Hamiltonian to understand and predict fundamentally interesting and technological important phenomena in real material. So some example of such phenomena are colossal magnetoresistance effect, multiferroic behavior, unconventional superconductivity, anomalous transport in itinerant frustrated magnet, etc. So his group presently more specifically interested in computation among different order parameter symmetries in effective Hamiltonian for superconductivity and cluster mean field approach, which is applied to quantum spin Hamiltonian relevant for low dimension magnet, and interplay of magnetic frustration and double exchange physics in spin charge coupled system. So he has been associated with innumerable national and international institute of repute. So it's a matter of great privilege to have such a decorated scientist among with us. So without much delay, I invite Professor Sanjeev to bless us with his pearl of wisdom for the last talk of this ESTC. Sir, please.
Thank you, Vinod. So thank you for such a kind introduction. Firstly, I see that this is the last talk of this workshop. I must actually congratulate Vinod and co-organizers for putting this together. This has been a very nice, meeting organized in such times, and I think it's excellent for students to learn from wherever they are. So this is an excellent step, and I attended some of the talks. I was not there in the Google Meet, but I was attending the talks in the YouTube, and excellent talks. So I must congratulate you guys for a successful program, actually. And so let me kind of come to the topic that I'm going to present today. So I'm going to talk about magnetic fermions in Rashba-Hund metals. The announced title would have read like magnetic fermions in Rashba coupled Hund metals. So this is, as I see that this is a workshop and it should cater to students, I will try to build that aspect in as much as possible. But nevertheless, since it is also the workshop title is current trends, so I think it is also my duty to explain or express some of the advanced topics. So therefore, this will be a combination of maybe a revision of elementary topics and so on, where maybe experts will not find it so interesting, but hopefully students can learn from that. And the later part or the second half of my talk will be presenting hopefully some new and interesting results, which even the experts may enjoy. So with that, let me begin with the presentation, and this is the outline of my presentation today. So if you notice that the title has these three keywords, Rashba, Hunds, and Skyrmions. So basically the task for me in the introduction is to introduce you all to these three concepts. So in particular, I'll talk about in the first few slides, what is a Hund's metal, what is the Rashba coupling, and what are magnetic skyrmions. So that will be the task for the introduction. And then I'll kind of go to more the motivation for what we are doing, which will be basically emerging from the observation of these magnetic skyrmions in experiments. So I'll discuss some experimental observations of magnetic skyrmions and also present the current status of their theoretical understanding. And then kind of I'll try to point out what is lacking in that current status of theoretical understanding, and we'll try to then introduce some microscopic electronic Hamiltonian approach to understand magnetic skyrmions. And this will essentially be done with the help of a simple, you can call it a toy model or a model on a lattice for electrons. So we will try to ask questions like, what are the minimal ingredients required to explain such complicated objects, such as magnetic skyrmions? And well, then the talk will go into sort of the new result aspect, where I'll present some new results on isolated and packed skyrmion states found in such microscopic electronic Hamiltonians. And if time permits, I would also like to emphasize or present the anomalous Hall effect emerging from the magnetic skyrmions, in particular the physics of electronic transport in the presence of magnetic skyrmion states. Okay, so let's begin by with the introduction by kind of trying to understand what is the what do these keywords Hund's metal, Rashba coupling, and skyrmions mean. So let's begin with something that I think everybody will kind of feel comfortable with. So this is Hund's first rule. So we all know, we have all read in the textbooks that elementary textbooks that for an isolated atom, when we try to fill the shells with an electron with simple principles, there are something called Hund's rules, and the first of those Hund's rules is that configuration with maximal total spin has lower energy. So if you want to fill a shell, you would like to put in electrons with the same spin orientation. So let's understand this with an example. Let's try to place 3 electrons in a D shell. So we know that the D shell has these 5 orbitals, and each of them can host an up and down electron, 2 electrons basically with opposite spins. And so if I want to place 3 electrons in the D shells, what can I do? Well, we can place these 3 electrons like this, right? So this is what Hund's rule says, that we should place the 3 electrons such that their total spin is adding up. And of course, this is an equally good configuration, right? But what about this? Well, this is not so good because the total spin is not maximum now. But if I go for this configuration, this is good as well. So this is also total spin is maximum. Okay. So the idea is that one should try to maximize the total spin. So this is the story of the Hund's first rule. Now, what about the second rule? The second rule says that the total orbital angular momentum should be maximized respecting the Hund's first rule. So what does it mean? Let's now again label these guys with their orbital angular momentum Lz in particular, the z component of the orbital angular momentum, and each of these shells has a Lz minus 2, 2 plus 2, right? So now Hund's first rule says, of course, that you put in the 3 electrons like this, but for the second rule, you would look at these Lz values and you would want the magnitude of that sum to be maximum. So therefore you would go for this configuration. And well, this configuration is equally good because this also maximizes the total orbital momentum, angular momentum, as well as total spin angular momentum. So these 2 rules by themselves also do not actually complete the story. So I'll come back to that. But the main idea of the Hund's rule is that the Hund's first rule and second rule is that the total angular momenta try to be maximum for the lower energy configurations. Now, what is the, one question is, what is the basic understanding, what is the basic physics behind these rules? And interestingly, this is actually an interesting read. And I would actually recommend all the students to take a look at Stephen Simon's textbook for this. So the key point is that these are all Coulomb interaction driven effects. And if I want to kind of oversimplify the story, basically, if there are two electrons with the same spin, then it is less probable that these two electrons will come closer to each other. And therefore, the Coulomb repulsion energy will be lowered if they are staying far away from each other. And hence, you want to have the spins, you want to have the electrons with the same spin orientation so that they don't end up coming close to each other. And it's the same story with the orbital angular momentum. So imagine a semi-classical picture is electron is revolving around, right? So that's different angular momentum states. And so if there are two electrons which are basically going around in a circular motion in the same direction, then they are less likely to have overlap with each other. That's roughly not absolutely exact, but that's the conceptual rough understanding of why the same orbital angular momentum direction and same spin direction leads to lower energy. Now, what is interesting is that, so far what we talked about, these rules are valid for an atom, okay, isolated atom in free space. Now we can ask the following question. Suppose I have an atom which has these three unpaired electrons, and according to Hund's rules, they would sit with their spins aligned, and I try to make a solid out of this. The first thing you notice is that this such a solid need not be magnetic. Okay, the magnetic moment, which is nicely present in an isolated atom, need not survive when we make a solid out of these atoms. And in fact, you think about it, this is a simplest example, perhaps of the famous more is different article by Phil Anderson, and I recommend all students, if you have not seen this, you have not read this article, this is an absolute must if you want to do science. So you must read this article. It's a 2-page article in Science, and I mean I cannot really overemphasize it enough that you must go back and read this article if you want to appreciate how science should be done and should be kind of viewed. Okay, so the key idea is that when you have an individual object and you have understood everything about that individual object, it doesn't mean that you can predict the properties of a large collection of such individual objects. And this is the simplest example that I have. So we have understood our individual atom. Individual atom is supposed to give us this magnetic moment of 3/2, right? Spin of 3/2, magnetic moment of 3 mu b. But when we make a solid out of this, that solid need not have a 3 mu b magnetic moment per atom. In fact, it will not have in most cases. And in fact, let me kind of try to explain it why. So the main idea is that competes with this so-called Hund's rule is the delocalization energy. So the basic property of a quantum particle is that left to itself, a quantum particle would like to actually delocalize or live over as much space as is available to it, and in this process it will lower its energy. I mean, if you want to convince yourself about this statement, you can ask what is the energy of the ground state of a particle in a box, and then you say that, okay, if I double the size of the box, what happens to the energy? So the energy of the ground state keeps lowering as you increase the size of this box. So essentially what is happening is that when you make a solid out of these atoms, these sort of d shell electrons, outermost electrons, have the possibility of delocalizing over the entire space. When these electrons are delocalizing over the entire space, both up and down electrons would want to take advantage of that delocalization, and therefore there will be no preference for a direction for the electrons. So up and down electrons will both try to delocalize equally, and hence the magnetic moment formation will be suppressed. So you will not see a magnetic moment in such a solid. Of course, if the electron interactions become relevant, so there is basically a competition going on between the kinetic energy, which is this delocalization energy, and the electron-electron correlations, which will try to then localize the electrons again. So it can actually happen that, and it happens in various multi-orbital systems, that this delocalization tendency is again suppressed if you have strong correlations, which means one can end up with a picture like what I've shown here. So if you, this is, let me just clarify, the x-axis is energy and y-axis is density of states, and up density of states is plotted with the weight in the positive side, and down density of states is plotted in the negative side. So in multi-orbital systems, it may happen that certain orbitals have a stronger localization, and therefore the Hund's rule is applicable for those orbitals. And so here I can point to this blue orbital here, which is a narrow band means a strongly localized orbital. So this particular band is consisting of strongly localized electrons, and therefore Hund's rule would apply to this particular orbital, and only one species of the electrons will be occupying this orbital. So the other orbital sits very far up in energy, the corresponding lower spin orbital. And if this is your Fermi level, then there can be a conduction band. Well, the conduction band is sitting right here by definition. And now you see that these electrons, these conduction electrons, effectively see a local movement coming from the partially occupied narrow orbitals. Okay, so these situations can happen in various materials. So one example is manganites, where T2G electrons form this spin 3/2 band, and the Ag electrons form conduction band. And this can also happen in a slightly different context in heavy fermion systems, F electron systems, where certain F shells can be half filled, and as we all know that half filling, again by virtue of the Hund's first rule, the half filled state is quite stable. So when you fill the F shell with 7 electrons, the 8th electron doesn't want to go there. It can even go to a 4s or 5p or whatever, but it would not easily want to go to the same 4f shell. So the 4f remains half filled, and it generates the effective spin 7/2. Now the Fermi level could actually lie in a different band, and therefore you have at the atomic scale, you have a magnetic field essentially available from these localized moments, which will couple to those electrons. So this is essentially this class of material that one can roughly label as Hund's metals, where the Hund's coupling has gone beyond the atomic level and is now applicable in the band. Okay. And this is a sort of a lecture notes article on arXiv, which the students can go back and read if you want to know more details about Hund's metals and multi-orbital systems and so on. Okay, so having discussed Hund's metals, now let's go to the second the buzzword in the title, which is Rashba coupling. And before talking about Rashba coupling, I would like to again go back to the concept of spin orbit coupling, and in fact to the Hund's third rule. Now notice that we have seen the Hund's first rule and Hund's second rule, and these first two rules did not give any kind of constraint on the spin angular momentum and the orbital angular momentum. And this is where Hund's third rule comes in. So Hund's third rule says that once you have applied the first and second rule, the orbital and spin angular momentum now either align or anti-align. That is sort of depending on if the orbital is less than half filled or more than half filled, they align or anti-align. And the origin of the third rule is actually in the atomic spin orbit coupling. It is not in the Coulomb interactions, but rather it is in the atomic spin orbit coupling. So let me briefly explain what is this concept of spin orbit coupling, what this concept of spin orbit coupling is. So imagine that we have an electron, and here is a positively charged nucleus. So this electron is basically, what is it doing? It's revolving around. It has a spin and it is revolving around this positively charged nucleus, right? Now you go to the reference frame of this electron and ask what you will see. This is what you will see, right? So if you sit in the reference frame of the electron, then it is the so the electron is revolving in the lab frame. In the reference frame of the electron, it is the nucleus that is revolving around the electron. Now, this revolution of the positive charge around an electron is essentially, you can think of it like a current loop. Yeah. So, roughly speaking, this is a current loop going around the electron. And current loops, we know, generate magnetic fields. So this current loop generates a magnetic field, and that magnetic field basically couples to the magnetic moment of the electron. This is the origin of the so-called L dot S coupling. So the spin of the electron has actually coupled to its own motion, right? So this is this picture of going to the reference frame of the electron is only for making the concept clear, but in principle, what has happened is that the electron spin has coupled to its own orbital motion, and that is what the L dot S or atomic spin orbit coupling is. And this is a relativistic effect, and this basically becomes stronger and stronger when your nuclei are heavier. So the coupling strength grows as Z to the power 4. So for heavier nuclei, this effect becomes significant, and this has been seen in experiments and so on. Now, what is Rashba spin orbit coupling? So this is coming back to the keyword in the title. So what is Rashba spin orbit coupling? Well, so let's talk. So let's say that in the previous example of atomic spin orbit coupling, we utilize the presence of the positive charge and its motion when we switch from the lab frame to the rest frame of the electron. Actually, that the presence of the positive charge or its details are not necessary, in the sense that if you imagine that there is an electric field present in the background, and a charged particle is moving in the presence of let's say a static electric field, then if you go back to the rest frame of the electron, you would actually see that electric field as a magnetic field, partly as a magnetic field also. So that's the relativistic idea that, in different frames, electric and magnetic fields are actually the same thing, in the sense that you can always switch the frame and see a electric field as a magnetic field and so on. So once you do that, you notice that once again, the electric field, which is seen now as a magnetic field in the rest frame of the electron, can couple to the magnetic moment of the electron. And this is what is called, this concept is utilized in defining what one calls Rashba spin orbit coupling. And so let me just, briefly mention when or in what circumstances it can appear. So you need to basically break the inversion symmetry along some direction in your sample. So for example, this Rashba coupling becomes very relevant at the interfaces between materials, or at the in thin film materials, or on the surfaces and so on. The reason being that on the surfaces or on the interfaces, there is certain direction in which the symmetry is naturally broken. The environment looks different on the two sides, and this breaking of the inversion symmetry is basically allows via symmetry arguments, it allows for the presence of an electric field. Okay, and if an electric, so you can imagine that there are electrons moving around in this plane, and there is an electric field which is aligned to the normal direction n cap, and that the presence of electric field in that direction is allowed because that there is a symmetry breaking along that direction. The environment below and above need not be same. And basically the Hamiltonian for that term can be written in this form, that the sigma vector is the spin of the electron, and electric field, the E is the electric field that is present in the surface along n cap, and basically E cross P cap is what the effective magnetic field looks like in the relativistic transformations. So the Rashba coupling will be sigma vector dot E cross P, and you can kind of expand it out, and you can, so basically a Hamiltonian of electron moving around, a free electron gas moving in 2D can be written like this, that there is a k square over 2m, the free electron term, plus this Rashba spin orbit coupling term, which the cross product Z component is what it is. So the n cap is along Z cap. And this effect was, of course, as the name suggests, was introduced by Rashba and together with Vishko in 1984. And a more recent article to kind of understand the importance of this effect in the modern sort of material science and also technology, you can go to this Nature Materials article. It's a very nice summary of what spin orbit coupling actually, what kind of things it is allowing to do nowadays. Okay, so we have discussed what Hund's metals are, and we have discussed what spin orbit coupling is. Now let me come back to the perhaps the main topic of the talk, which is magnetic skyrmions. So the term skyrmion emerges from this old paper in nuclear physics by Tony Skyrm, who presented a theory of nucleons, basically. And according to his theory of nucleons, so he wrote down certain field theory called nonlinear sigma model. And when he analyzed the solutions of this field theory, there were some solutions which basically appeared as rather complicated textures in real space, in the sense that this particular field was a three-component scalar field, and when you look at the solutions and ask how each of the components is varying in space, it turns out that they make some complicated patterns. So now, so I'll kind of come back to those patterns in the modern context. So let me, basically say what magnetic skyrmions are. This is the motivation that this concept of skyrmions has emerged in some sort of a, you can say, a mathematical physics or high energy physics ideas, which have been lately realized in actually materials, in magnetic materials. So magnetic skyrmions are again these stable topological textures in magnetization profiles. So what was proposed in this nonlinear sigma model theory has been actually seen as a texture in the magnetization profiles. Now, what is the connection? The connection is this theory was written for a three-component scalar field, and so here a magnetization can be thought of as a three-component object. So magnetization is a vector at each side. So the magnetization field is basically is a three-component object. So X component, Y component, and Z component of the magnetization can vary in a very complicated way. So and such complicated variations have been seen. And let me actually show you the pictures, what one means by that. So this is the complex structure that one is talking about. So let me, maybe to express the key ideas, let me go through this picture carefully. So in magnetic materials, two kind of skyrmions have been reported. So one you can call Neil skyrmions, or they are called Neil skyrmions, which look like this, and the other is what is called block skyrmions. Now let me go back to this picture and explain it, take 1 minute on this. So look at the configurations on the circumference. So all spins are pointing up. And if you go away from it, everything will keep pointing up. So it's like a ferromagnet out there. But when you come inside this, the spins have started tilting. And eventually at the core, the spin is pointing down. Okay. So this can be seen like an excitation in a ferromagnet. Okay. And what is the Neil character? The Neil character is that if you come to a certain circumference where all spins are pointing in the XY plane, the Z component has gone to 0, then the orientation of these spins is along r cap direction. So that's the Neil skyrmion. On the other hand, if you look at the block skyrmion, the spins are orienting in such a way that they are also having a angular character to that their orientation. And if you come to a point where the spins are in plane, their orientation is actually in theta cap direction. So that's the key difference, that you have in the Neil skyrmions, your spin modulation is such that it is the projection is always in the r cap direction, whereas in this case the projection, the in plane projection, can be or is in theta cap direction, can have some component in the theta cap direction. And here you can, so these are also called chiral skyrmions because you can define two chiralities now. They can be rotating like this or they can be rotating like that. So even for Neil skyrmions, there can be two objects. One is they are pointing in the plus r cap direction, or others can be pointing along minus r cap direction. And so just a fun sort of a geometric or mathematical fact is that if you take one, you can do it as a stereographic projection from a 3D hedgehog. So you take a sphere, and on the surface of the sphere, you place spins which are pointing radially outwards in the 3 dimension. And now you take the south pole of this, where the spin is pointing down, and map it to the center here. And then you basically do the stereographic projection of each spin. Then it will essentially map to this object. Okay, so, and as I said that these have really been observed in experiments. So let me share some slides on the experimental observations of these objects. So here is a spin polarized STM picture for iron multilayer shown on iridium substrate. This paper came in Nature Physics in 2011, and the idea of spin polarized STM is that your STM tip has a particular magnetization direction, and therefore the tunneling spectra would have would be, you will be able to map the magnetization of the underlying pattern looking at the tunneling spectra. And this is the picture that you can kind of one comes up with after doing this STM experiment. And as you can see that there are these objects, that this is a spin which is having no component in plane. This is completely pointing up probably from this picture. And then as you go outside, the spins start pointing in plane, and then they turn down and so on. So this is actually what is called a skyrmion lattice. So there is a periodic arrangement of such objects. So this is a skyrmion lattice, and the scale is shown here. So this is 3 nanometers. So essentially each skyrmion size is like 2 nanometer, 1 nanometer, and so on. So essentially the scale is 3 nanometers. So very small sized objects. In fact, these are also called nanoskyrmions sometimes because they are at the nanoscale. Then another tool that is used successfully to kind of map out such complicated textures is what is called Lorentz transmission electron microscopy. And if you look at, so this is the data of LTEM, Lorentz transmission electron microscopy, on cobalt, zinc, manganese alloys. So what you notice is that in the absence of the magnetic field, you will see this stripe-like pattern. So magnetization is doing this modulation. And once you apply magnetic field, you will see such textures appearing, which are interpreted as magnetic skyrmions. Now, this is of course backed up with the small angle neutron scattering data. So, typically neutron scattering basically maps out so it's like a structure factor calculation. So it maps out the periodicity in the background, right? So if you do a neutron scattering experiment and you find a sharp peak somewhere, that means that there is a periodic organization of the background real space texture, and the reciprocal vector corresponding to that periodicity is showing the peak. Now in skyrmions, what would happen is that you would see multiple peaks. The reason being that each component of magnetization is modulating differently, and each component of magnetization can actually generate its own location for this peak, which can be different. And therefore, typical signature for a skyrmion lattice would be such multi-peak structure in the small angle neutron scattering data. So this picture corresponds, this arc-like pattern of the SANS of data corresponds to this picture over here. Okay. So in fact, let me point out that if these were absolutely straight stripes, then you would get 2 sharp peaks here. The reason that you are seeing arcs is that these objects are not perfect. They are modulating a little bit left and right, and that is showing up as a location changing slightly. Okay, the fact that the radius of this, so this you can think of this as an arc on a certain radius. The fact that this magnitude remains same is actually telling us that the width of these objects don't change. They simply reorient like this, but their width doesn't change. And well, so in addition to this, there have been like more modern techniques where something called X-ray holography, which I don't know much about actually. So which have been used lately to map out these skyrmion textures. And this is a Nature Communications paper of this year. So the key features or the common features in what I discussed in the last 3 slides is basically that these in the absence of the magnetic field, you typically see such patterns of the magnetization orientations, right? So this is so-called spiral phases or stripe-like phases. So you see this consistently, you see these phases, and when you switch on magnetic field, you would see a skyrmion lattice formation. And other thing that I kind of want to point out from this is that most of these materials that have found that are kind of presented as hosts of skyrmions are containing materials which have a large magnetic moment. So these are iron, manganese, and so on containing materials. So with this discussion of the experimental observation of skyrmions, now I would like to kind of ask what is the theoretical understanding of these textures, how in theory we understand the formation of these textures. So
can I ask a small query? What is
yeah.
the statistics of skyrmion?
What is the
statistics? What statistics they follow? Fermion or boson?
Yeah, that's a very well. It's actually not a very simple question to answer. So so first question can be that can you think of skyrmion as a particle?
Quasi particle.
Yeah, so it's a quasi particle, and if, for example, if you compare with, if you think of the skyrmion as an excitation in a ferromagnet,
yes,
then it can be thought of as some combination of magnons. In fact, that is what the prevailing picture is. So this is basically certain combination or a multi-magnon bound state, and therefore they should follow bosonic statistics. That is the. But I think the question is not to at least in my opinion, it has not been well answered in the field.
But it is an emergent excitation, no?
Yes, it is an emergent excitation. Yes. Yeah. So there have been there are some papers where they even claim that certain BEC of skyrmions can also be observed. So it hints towards skyrmions being bosons, but I think this question has not been really convincingly answered, in my opinion. Does that
maybe it is irrelevant? Maybe it is irrelevant. I don't.
Yeah, I mean, actually, it's an interesting question. I think it's kind of worth investing in this question further. So maybe we can discuss offline sometime.
Okay.
Yeah. Right. So so if you think of the theoretical understanding, so for a long time, actually, the skyrmions were basically understood, or these patterns were basically understood with the help of continuum models of Ginzburg-Landau type. So one writes a Landau free energy functional, and the standard magnetization dependent terms plus some gradient terms, and if you introduce certain complex gradient terms in this in the free energy functional, you can show that such functionals would also stabilize skyrmion textures. So as recent as 2006, this was the understanding of skyrmions, but more recently people have actually started to ask whether you can write down lattice spin models, explicit models of the type SI.SJ or some other terms, where you can show the skyrmion formation, and this has been also successful. So the idea is that if you consider Heisenberg term and so-called Zylshinsky-Moria term, which is a cross-product term between spins, then it is possible to show that skyrmions can exist even in such lattice models. And even more recently, what has kind of become interesting is that people are trying to ask whether you can write down microscopic electronic Hamiltonians where you can kind of define or show the existence of skyrmions. So there has been some success in that direction recently, and this is one paper where they look at a triangular lattice and some certain pattern of hopping parameters on triangular lattice with the Hund's-like coupling, and they show that the skyrmions can form in this model. Now, basically, so let me kind of summarize on this slide the gaps in the theoretical understanding of the skyrmion formation, And so the first question is that when one tries to write down the spin models for metals, then they can be questioned in the sense that metals are objects where electrons are flowing around. So there is no, unlike insulators where the mobile degree of freedom of the electron is gone, and you only have now the orientational degree of freedom left, which means you can talk meaningfully about the spin models. But if you have electrons moving around, talking about spin models is something that can be questioned. Let me just try to switch off my fonts. Yeah. Am I audible? I just want to make sure that I'm online.
Yes, yes, you are audible.
Okay. Okay.
Part of
So,
your mic is muted. You want to ask?
is there a question? Please go ahead.
No, it's okay. You please
Okay.
go.
Okay. Yeah. So for the questions, I would again say that I have put these slide numbers. So if you have questions, please note down the slide number so that you can always come back to that slide later. All right. So one point is that writing down spin models in metals is a questionable thing, unless one can justify it, of course. Then most theories explain existence of skyrmion crystals and not the existence of isolated skyrmions. That is another feature that has been missing in most theoretical models. And the third thing that we saw in the experimental data, this arc-like pattern in the small angle neutron scattering experiment and the related domain wall pattern. So there have not been explanations of these arc-like patterns in literature, as far as I am aware of. And so the only attempt to look at this electronic-based understanding is what I mentioned on the previous slide, this paper where they look at a triangular lattice and they also assume a weak coupling between the localized electronic spin and the conduction electron and so on. So given this status of the understanding, now essentially so we start discussing from here onwards what we are trying to do. So let's hope that I can keep it again to an understandable level. So let's begin with the simple model, which is also written down by these other authors, that you have a kinetic energy or a hopping term for electrons and a local coupling to a magnetic moment of the conduction electron. So basically, there are two degrees of freedom that one is talking about in this model. One is these red objects, which are electrons, and these electrons can essentially hop around. And the other is this local spin degrees of freedom, which can orient. So these guys cannot move around; they can only reorient at the same site. So this is the point, that electron can move around and the spins can rotate. And this Hamiltonian describes the physics of these two degrees of freedom, that at each site, the electron spin is coupled to the corresponding localized spin via Hund's rule-like coupling. And this electron can move around. So notice that in this model, there is no coupling between the spins. Now let's add to this the spin orbit term, and this is the same term that we talked about, the Rashba term, written in the electronic operator form, and this is what it looks like in the electronic operator form. And so if you actually look carefully at this term, this says that electron can be destroyed at a site J and created at site I with the same spin orientation sigma. Whereas this term, the essence of this term is that electron, when it moves from site I to I plus X or I plus X to I, it also changes its spin. So, visually, that is what it means. So this red electron, when it is hopping from site to site, it is also turning around. So that is the essence of the Rashba coupling in a lattice model. So a normal kinetic energy generates a spin preserving hopping. So the spins just remain the same as the electron goes around. And the Rashba coupling generates this spin flip hopping. So the hopping occurs simultaneously or together with the flip of the spin of the electron. Now, the question we ask is that how difficult is it to understand such a Hamiltonian? How difficult is it to, for example, find out the ground states of this Hamiltonian? And this is where I can begin with this, the question on a simpler Hamiltonian. So let's not worry about the Rashba coupling right now. The question is equally kind of valid for this Hamiltonian as well. And so the answer is the following: that if you want to treat this problem in its full quantum mechanical glory, which means you want to treat the localized spins also as quantum mechanical operators and the electrons also as quantum mechanical objects, then you encounter the problem of the large Hilbert space and exponentially growing Hilbert space. And essentially, there is very little you can do unless you find some clever approximations in certain limits. There is very little that one can do with such Hamiltonians. So if you're looking for a general solution for all parameters and in any dimension for this kind of Hamiltonian, then you have to look for approximations. And one approximation that we can kind of utilize in the present context is that the localized spin typically can have a larger magnitude, which, as I mentioned, in all these fermion materials, the magnetic moment on the iron element or manganese element and so on, these magnetic moments are large. So once you have large magnetic moments or large spin, you can say that, well, I have a Born-Oppenheimer-like situation where I have my fast variables, which are electrons, and slow variables, which are spins. So the problem basically, or the problem can be divided into two parts. So question one will be, what is the ground state of the localized spin subsystem? So how would these localized spins like to orient or arrange themselves? And question two would be, how do the electronic properties get affected by those magnetic states? Okay, and a formal answer to that question, or these questions, is that basically you can write down the partition function for the full problem, and then you can define an effective Hamiltonian, which formally is, the definition is like this, and therefore using that effective Hamiltonian, you can kind of proceed and answer question number one. And once you have answered question number one, question number two is rather trivial, because you just have to, question number two essentially is solving the one electron problem in the background of given magnetic state or magnetic arrangement of these spins. But this expression written over here is kind of misleading in the sense that this is only a formal step. This doesn't help in any way. Well, it can help in some cases, but in general, it doesn't help. But it actually motivates a numerical scheme. And this is what kind of we have used for this problem. And it is a very useful scheme for such problems anyway. So the idea is that if you want to, so let's kind of recap. If you had a closed form expression for a Hamiltonian in terms of spin variables, you can perform what is called classical Monte Carlo, which means given a configuration of these magnetic moments, you would know what is the energy of that configuration, and you can then calculate, reorient a spin, calculate its energy, and go through the Monte Carlo Metropolis algorithm to update your configuration. Now, in the present problem, there is no closed form expressions available for the spin configurations, for the Hamiltonian for a given spin configuration. Instead, what you have to do is you have to diagonalize the fermion problem for each configuration. So you take a spin configuration, you solve the Schrodinger equation for electrons in that configuration. That gives you the energy of the configuration. And then when you reorient the spins, you have to again solve the corresponding fermion problem, and that gives you basically the energy difference of the configurations which you utilize in Metropolis algorithm. So the idea is that, so this is what is called a hybrid Monte Carlo simulation method, where it's a combination of Metropolis algorithm for classical variables and a fermion diagonalization for the electronic variables. And this algorithm is kind of rather heavy, not exponentially difficult, but it scales as n to the power 4 with number of sites n. So one cannot really, problems like fermion formation where you need modulations over large scale and complex modulations, it will not be really helpful to kind of use this method alone. So therefore, we look for trying to find the effective Hamiltonian. So this idea, can we find out a closed form expression for this effective Hamiltonian for spins? And one limit of this, again, for the students' benefit, I can just present this slide, which experts can completely ignore, that if you have magnetic moments sitting in a metal, then we know this famous RKKY theory that the electrons can mediate an effective interaction between those magnetic moments. And this RKKY theory is nothing but a perturbation theory in JH by T of the Hamiltonian that we had written down. So, and once you write down within the RKKY theory, the Hamiltonian would look like this, that a spin at site or location R is coupled to a spin at location R plus R, and the coupling constant is a distance dependent object. And in fact, the coupling constant has a very strange modulation of sign as well as magnitude. So this is RKKY theory, but this works only when JH is small. So the Hund's coupling has to be small for this case. So can we, what can we do in the large Hund's-Rule coupling? So in the large Hund's-Rule coupling, apparently there is another very, nice idea, again going back to 1950s, which is called double exchange mechanism or double exchange physics. So I think this is conceptually a very important slide. So let me spend some time on it, on this slide, even if I have to rush through the later slides. So let's stare at this Hamiltonian for now. Again, this is the same Hamiltonian. I'm not worried about the Rashba coupling inclusion here. So this is just the electron kinetic energy and the local Hund's-Rule coupling of the electrons with the local magnetic moments. So imagine a situation where the local spins are oriented like this. Now this Hamiltonian is written in such a way that my electron is represented by a global up or down index. So there are two types of electrons, up electron as well as down electron. This is what is called a global quantization axis notation. I can go to a local quantization axis notation, and in that notation, the two states that I will use locally are the ones which I call parallel and anti-parallel. But notice the parallel and anti-parallel state at this side is different from the parallel and anti-parallel state at that side. So this is why it is a local quantization axis. So each site has its own quantization axis orientation. Now over here in this picture, within this Hamiltonian, this down electron could only hop to the down electron, and the up electron could only hop as an up electron, which means spin preserving hopping. In the parallel anti-parallel picture, this is not going to be true anymore. So because you have basically, mathematical idea is that you perform these local SU2 transformations and at these two sites, and as a consequence of these SU2 transformations, your effective hopping will modify. So basically, the parallel electron here can go to the parallel electron here. The parallel electron here can also go to the anti-parallel electron there, and so on. And these magnitudes of these hoppings, these different hoppings, will depend on what is the orientation direction of the background spins or background magnetic moments. Now, keeping this picture in mind, so basically, if suppose I don't worry about this term, then the Hamiltonian is completely independent of the representation, in the sense that it's the same Hamiltonian that we are representing if we are keeping all the terms here. Now, let's kind of make use of this. And to make use of this, we argue that if this Hund's-Rule coupling is very large, then the parallel and anti-parallel bands would be separated by an energy scale which is order JH. And if this JH becomes extremely large compared to the hopping parameter, so the bandwidth is roughly, let's say you can think of the bandwidth as the hopping proportional to hopping parameter, and the separation is this scale Hund's-Rule coupling. So if this separation becomes much larger than the bandwidth, then you can completely ignore the upper band and you can work completely in the parallel band. And that is what I've tried to indicate here, that you can basically focus completely on the hopping between parallel and parallel spins. Okay. And what is the double exchange mechanism? Double exchange mechanism exactly relies on this idea that if I have, so imagine that you're working in the strong Hund's-Rule coupling limit, then if I have two spins which are parallel, then the electron can hop perfectly fine between them. So this hopping amplitude will be same as the original hopping amplitude T. On the other hand, if the spins are oriented like this, then this electron, which is parallel here, has to become, so the parallel component over here is sitting at very high energy, because the parallel, the parallel component here is actually, so this has to become anti-parallel here. So the low energy sector here is anti-parallel, and this up electron cannot turn into the down electron. Okay, so therefore this hopping will be completely missing, and this will generate an effective spin Hamiltonian, which will look like this. And in fact, if you kind of maximize this term, you would find that so this denotes the tunneling amplitude, effective tunneling amplitude, and the tunneling amplitude has to be maximized to minimize the energy. So remember again the delocalization physics. So the electrons want to delocalize as much as possible left to themselves, and now the delocalization extent is proportional to the tunneling amplitude. So larger the tunneling amplitude, larger the delocalization. Therefore, the tunneling amplitude becomes dependent on this orientation of these spins. And if you can find such an orientation where the tunneling amplitude is largest, then that is the best orientation, best configuration that your system would like to have. Okay, this is actually, there is a very nice similarity with what one, encounters in or discusses in metallic bonding. So it's the same idea, except that it is now being applied to the orientations of spins. Right. So having kind of spent enough time on this slide, now it's sort of a slightly technical point that we can include the Rashbach coupling and perform the same mathematical task of SU2 transformations and finding out what these effective hoppings are and so on. So this is kind of now coming to more to our recent work. This is what we find, that you can have an effective hopping, which is basically denoted as G, and this is a combination of T and lambda terms. So the T term gets modified and the lambda terms get modified and so on. And you notice that lambda has a direction dependence. And going ahead with the same, I want to make sure that the students do not, lose their way in the technical details. So it is essentially the physics of this slide that we are applying on the full model, where the spin orbit coupling has also been included. And that doesn't actually complicate the process conceptually. It only complicates the process technically, in the sense that the maths has to be done a little bit carefully and so on. So I can now sort of maybe go a little fast. And so if you, along the same lines, if we try to derive an effective spin model along the lines of this effective model, in terms of the tunneling amplitude being maximum and so on, then we obtain actually this particular model. So the spin Hamiltonian is some coupling constant times this function Fij gamma. Gamma denotes the direction, which means Fij along x and Fij along y are different. And the expression is written like this. This is the sum. This is the compact form of the expression. If you expand it along one of the directions, it will basically look like this. So it's a rather complex looking expression, but the physics is very clear actually once you look at these terms individually. In particular, this is the same old term which appears because of t square. Then there is a term which appears purely because of lambda, which is proportional to lambda square. And then there is a mixed term which is t into lambda. And notice that this t into lambda term is very much like Zelsinski-Moria coupling, which people use in their effective spin models. And the x and y directions are of course coming in handy here, or becoming important here. So the gamma prime defined here is actually z cap cross gamma. So gamma prime becomes y for gamma equal to x, and it becomes minus x for gamma equal to y. Now, so beyond this, essentially what we do now is we simulate this model on a lattice. And this is a comparison. This is kind of just to convince ourselves that the calculations are being done correctly. We compare the results of this hybrid Monte Carlo simulations and the effective spin model that we derived. And we find that in the low temperature region, essentially the results match very well. So now, having kind of discussed what the effective Hamiltonian looks like and what the method is that we can use to study the physics of this Hamiltonian, let me just spend one slide on the order parameters. So basically, the main order parameter that we use, or one of the main order parameters that is used, is a component resolved spin structure factor. So spin structure factor essentially is a Fourier transform of a spin-spin correlation function, and the mu denotes the x, y, and z components of the spin. So again, remember that there are these two spaces involved here. So the real space is a two-dimensional space with x and y directions, whereas the spin space is a three-dimensional space where the spin can take three components, x, y, and z. So this mu refers to the components of the spin. So you can define basically the structure factor for each of these components separately, and the total structure factor is then sum of the all components. And just to kind of give a very brief glimpse of what this guy measures. So if I have a ferromagnetic order, then the spin structure factor will show a peak at q equal to 0. So at q equal to 0, it will have a peak. If the order is antiferro type, then the structure factor will show a peak at pi by a. And if you have an order which is slightly more complicated, which this will become relevant actually in this fermion physics, if you have a spin order pattern which shows a spiraling like texture, so you notice that this spin here is orienting slowly as you go along the positive x, and it comes back to itself over here, which means you can kind of define a wavelength for this pattern, for this wave, and the wavelength is lambda. Then the spin structure factor calculation performed on this particular object will actually show a peak at q equal to 2 pi by lambda. And what will be kind of more interesting is that in the fermion cases, different components of this structure factor can show modulations of different wavelengths, and that's what this multi-peak texture or multi-peak behavior of the spin structure factor will be. So having understood this, now I can just quickly present the results. Once again, I mean, at this stage, I would like to say that the main motivation and the theme of the field is probably already presented. And now what I'm going to show is some of our calculations, which again, you can find interesting. So this is one such order parameter where one shows only the 0, 0 component of the Q of the structure factor, and this is basically measuring the ferromagnetic order. So this is essentially an order parameter for a ferromagnet. In fact, this is related to magnetization itself. Then you can show the one can look at a different component, some Q. Q is not specified here. So at certain Q, which is neither 0 nor pi, one can have this rise in the order parameter, which shows or which measures the spiral character of the spin configuration. And similarly, you can find situations where different mu components, so remember that there's SF had a mu component, so different components of this show different behaviors, or rather show simultaneous rise. And this is the multi-Q object, which will be interpreted as fermion lattice, and we'll see explicit real space images of this fermion lattice. And similarly, you can have a planar multi-Q state, which is known as flux state, and so on. So here you have simultaneous peaks at 0, pi, and pi 0. So these are various interesting structure factors that come out from the Miltonian simulation. And now I can just present a phase diagram briefly here, which is, so alpha measures the strength of Rashba coupling. And this is temperature versus alpha phase diagram, where you start with a ferromagnet at alpha equal to 0, and you get into a phase what we call classical spin liquid, which I'll describe briefly, and then into a spiral phase, what is known as a single Q spiral phase, and then into a multi-Q spiral phase, which is basically fermion crystal, and finally a diagonal flux phase. Now, the structure factors in these different phases are shown here at different alpha. So I would simply like to basically point out the two structure factors images belonging to the green region, classical spin liquid. They in fact look like this. So the structure factor shows a ring-like pattern here. This is alpha 0.25 somewhere here. And if you go close to the boundary, this starts showing arc-like features at the 4 axial points. And finally, this becomes a single Q state, and then it becomes a multi-Q fermion state, and then it becomes a 0 pi pi 0 kind of a planar flux state. The advantage of real space simulations is that we can actually plot the spin textures themselves, and that's what I'll show you now. So these pictures are showing on a very large lattice. This is probably 200 by 200 and so on, and maybe 60 by 60. So on this lattice, the color coding is representing the Z component of the spin, and the XY component of spin are represented by the arrow orientations. Okay. So these two are the pictures for the classical spin liquid. So this filamentary objects moving around, domain wall like objects, is what is seen in this classical spin liquid. And
Ele băitul suor, negocia lago nia.
so this is a single Q state, spiral state, and notice that here spins are spiraling in the YZ plane, because color code changing means the Z component is changing, positive and negative, and the orientation is in this direction. So this is the YZ plane spiral, and this is what a multi-Q state looks like, which is basically a skyrmion crystal. So this picture, and you can compare with the first experimental picture that we had seen, that a central spin pointing down, then there are spins which point in plane, and then it sort of fades away, and then, but before it fades away, because this is not an isolated object, the next object comes in. So it's a periodic pattern of such skyrmion or nanoscale skyrmion textures. And then this can be slightly more complicated, where this is essentially a larger radius skyrmion, and then finally it can become a planar flux state. So I can essentially, so what we found interesting here, which maybe I can skip for the first introduction, is the origin of these filamentary reorienting spin textures is very interesting. And this is essentially this classical spin liquid, which is orientationally symmetric. So the explanation for this was that we have a degeneracy of states where the spin spiraling in the XZ plane and the spin spiraling in the YZ plane can have the same energy if there is simultaneously a change in their Q vector. So this is what essentially it's shown in these plots, that we set up a variational calculation for the spins and show that the energy for different spin configurations with different orientations of the spiraling plane and different Q vectors, corresponding Q vectors, end up with the same energy. To kind of put this in a very simple way, what it means that if I have a spiral plane like this, and suppose the plane is XZ, then the spirals would like to go along X direction. If the plane orients in the YZ direction, then the spirals travel along the Y direction. And similarly, a different spiraling plane can have a different Q vector, but all of them have same energy, which means that the orientations of the filaments or the domain walls is completely free of energy cost. And this is what is the picture here, that these filaments, when they are reorienting in any arbitrary way, more so here, then this is happening because they are not, it doesn't cost any energy essentially to bend these filamentary textures. And that is why this state is presenting such a circularly symmetric structure factor pattern, which is a liquid-like feature. And so maybe you can just watch. Let's see. Vinod, how much time do I have?
Still 20 minutes.
Okay, that's great. Yeah. So we can just maybe you can just watch this movie where we show how lowering temperature, starting from a paramagnetic configuration, and you simply lower the temperature in the Monte Carlo simulations, how exactly this skyrmion crystal emerges. So this is one example of that. So basically, you notice what is happening here is that if you go along this line, this is, let's say, mostly it is a spiral in the xz plane. Okay, so spins are pointing down, then they're going in plane, then and so on, and going out of plane. And if you go in this direction, it is a spiral in the YZ plane. So let me kind of go back and we just point out the origin of this interesting effect. So the origin lies in this term. So you have a gamma prime cap dot s cross si cross sj interaction, where gamma prime is y for the x direction bonds and minus x for the y direction bonds. And what it means is that this term, in order to kind of lower the energy due to this term, the spins should orient themselves in either xz plane or yz plane, depending on whether you're going along x direction or y direction. And simultaneous satisfaction of both these is not possible, because the spins are after all common. So a certain spin wants to be, this spin wants to be part of this spiral, and it also wants to be part of a YZ spiral. It cannot do both, and therefore there is a strong kind of frustration or competition kind of effect going on, and a consequence of that frustration or this competing effect is the formation of such textures. So far what I have discussed, actually I have not included the magnetic field in the Hamiltonian. And now in the next slide, or next few slides, I'll just show you the results when magnetic field is also included. So we don't need to worry about the technical details now, because the inclusion of magnetic field is very simple. You can simply add a Zeeman coupling term with HZ, SZ kind of a coupling, and this can be either handled within this hybrid Monte Carlo approach or within the effective spin Hamiltonian approach. And it's basically, I'll just present results for the effective spin Hamiltonian approach here. Although we have tested the results for both the approaches and they match very well. So when we kind of include magnetization, then we also build in certain other order parameters, namely the skyrmion density order parameter, which is basically a lattice version of this continuum definition of skyrmion density. And similarly, we build in a chirality order parameter and so on. So here in this picture, I would just like you to, instead of trying to explain everything, so the blue line is magnetization, and as expected, the magnetization. So as you increase magnetic field for different Rashba coupling values, the magnetization is always going to increase. So the magnetization shows the standard increasing behavior. But the main quantity of interest is this red object, which is the skyrmion density. So you find that close to the saturation magnetization, you have a rise in the skyrmion density. Similarly here, this rise in skyrmion density occurs even earlier here, and so on. So from this, what one can read out is that as you are applying magnetic field, beyond a certain critical value of magnetic field, skyrmions are forming, well-defined skyrmions are forming. And let's maybe look at the textures now. So remember, this was the magnetic pattern in the absence of magnetic field. And when you apply field, then basically these filaments break into such objects. And this is a zoomed in version. So you have a central spin which is pointing down. Then the next next set of arrows in a certain radius are going down and inwards. So their planar component is becoming finite, and so on. And then they become completely planar here. And eventually, when you go away from it, this is the orientation of the spins is in the plus z direction. That's the z component with the yellow color code. So the yellow region is essentially a ferromagnet, and then these objects are sitting there as some kind of defects in the ferromagnet, but topological defects with a certain well-defined topological characteristic. And so starting with different values of spin orbit coupling, you can actually get different textures. So this is what we call isolated skyrmions, because there doesn't seem to be any close packing of these objects. If you start with a different value of the spin orbit coupling parameter, then one obtains these so-called packed skyrmions. And as you increase magnetic field strength, these objects can become smaller in size, and then they can even they melt away, they go away. And this is the example of one of the skyrmion crystal pattern in the presence of magnetic field. So again, here I think I have a movie here which shows how increasing magnetic field, these filaments break into skyrmions. So let's just watch this. This is a heavier file, so I think there is some problem with the playing, but it's okay. The main idea is clear. So you notice that, let me just. So now you see already that some objects have formed here. And eventually, all of this filament is going to break and lead to a set of skyrmions. For example, here I can pause it. And now if I keep increasing magnetic field, what will happen is that the peripheries of these skyrmions are being polarized, which makes sense, right? Because these are easier to be polarized. So in the periphery of the skyrmion, the spins are getting polarized slowly. And finally, the entire skyrmion sort of structure will vanish because your field that you applied is so strong that it's sort of everything is polarized. Right. So, and we can, again, this is the phase diagram in the presence of magnetic field. So we get two kind of patterns in the structure factor. One is like this, which is this packed skyrmion structure with the hexagonal packing structure. And other is this skyrmion lattice, which is this small pocket here, where you have a pattern which was shown earlier, this kind of pattern. And to show another example of formation of the skyrmion crystal, here is a movie which starts from this line and goes up like this. So you are starting from a single Q spiral state where spins were pointing in, were spiraling in the YZ direction, and now you are changing magnetic field along this axis, and let's see what happens. So in this case, basically what happens is that the entire skyrmion crystal sort of emerges almost simultaneously. So unlike the earlier case where individual objects emerged, one by one, here essentially the entire crystal emerges instantly almost. And one measure of this is this parameter, skyrmion number, which is just the, this is the skyrmion density essentially. And this shows a sudden jump to a large number. And then notice that it remains flat. It doesn't change, which means this is a packed structure of skyrmions. You just cannot fit any more number of skyrmions now. This is the number that you have got. And finally, as you keep increasing the magnetic field, these skyrmions will melt away. And again, the melting will be almost instantaneous because there is essentially no, the region in field over which this goes away is very, very small. So this sharply drops down. So they almost immediately melt.
Sanjeev, can I ask you one question here?
Yes, please.
Can we understand, is skyrmions as a particle? Can we understand as a particle?
Skyrmion as a particle. Hello, did I get your question? Yeah, so this is, I think, related to the question that Professor Pathak asked earlier. That so there are actually two levels at which you can talk about something being a particle. One is, for example, this is essentially let's look at this object, right? This is a well-defined pattern. So visually, it looks like an object, and if I can drive this object with some external measures, right? Suppose I apply magnetic field, electric field, or whatever, and I am able to move this object in a certain way, then it is a good enough reason to define it as a particle. That is, it is an object which will retain its characteristics and it will respond to external stimulations, right? So that's one way of defining particle. But then, if you want to take that definition seriously, then we have to come back to this question of the statistics of the particle. If we want to define it as a quantum particle, and that is where the trouble begins. I mean, so I think at the level of defining it as a classical particle, there is no problem. This is actually a a stable classical particle-like object. But defining it as a quantum particle has more issues. So I mean, I think that's the answer. That classical particle is completely fine, but not quantum particle.
So is there any experiment related to this? Is it theoretical?
Yeah, there are many experiments where they have actually shown. So these skyrmions are coming up in the big way as kind of the data storage devices and so on. And there are many experiments going on where they try to drive these objects on what is called race tracks, and then try to define a qubit or a bit from that. So there are many experiments going on. I can share with you the details, the references and so on later if you're interested.
That means classical experiments will be classical, like scattering experiments.
Yeah. So basically, these objects, so since these are like magnetization patterns, so these are essentially can be thought of as classical experiments.
By neutron scattering or something else? Inelastic neutron scattering? Inelastic neutron scattering?
Yes. So the patterns are kind of seen by neutron scatterings as well. And the driving of these objects is done with the help of currents actually.
If you can do the simulation dynamics, you will know whether it is a particle or not.
Absolutely, yeah. So what is so that absolutely right.
Even small system will be good enough to prove the statistics and whether it's classical or quantum.
Yeah,
if you can do the simulation.
Right. So one point is that most of the
simulation is simpler for classical system.
So this simulation is treating it as a classical system. So the simulation that we are doing,
you can do that.
Right.
So you can do time dependent also.
Yes, one can do time dependent. That will tell us whether it is actually
right. Yes.
Yeah. Any other question at this stage, or I think there's just one more topic or subtopic that I needed to discuss, which and then right. So maybe let me complete and then we can come back to and close to the finish. So so remember we started by asking two questions, that this very complicated looking Hamiltonian. Yeah.
Can I ask one question? I'm Dr. Kiran from IIT Jalandhar.
Hi.
Right. Nice talk. Sanjeev, I want to know that how the fermions are different than magnetically field-induced phase. Because if you apply the magnetic field, then the magnetic state may also change in magnetically induced phase transition. So how they are differ from such things, fermions? Because experimentally, sometimes the behaviors may look like same. So what could be the confirmation that it is fermion experiment?
So experimentally, as I said, that one has to create a 3D map of the magnetization patterns. And that actually is not so simple. So these L-time experiments and their combination with the small angle neutron scattering, that seems to be the most convincing way right now in the experimental community to confirm that they are fermions. So if you have a 3-dimensional map of the magnetization pattern, and you see that all components of magnetization are showing some non-trivial variations in the spatial directions, then you can one can then quantify it as a fermion, in the sense that, well, so, or to answer it mathematically, you need to basically compute this object for your magnetization pattern. And if you find that this is having a non-zero and integer values for such ideal fermion-like regions, then it is a fermion. And you can do it from the experimental data also. So you present one arrives at a map of the magnetization vector profile, and then from that profile you can do the calculation of this object and try to quantify this so-called winding number for the fermion. So if this topological measure turns out to be finite, then it's a fermion. Well, that seems to be the present definition. So this will not happen in with magnetic bubbles and the ferromagnets and so on. Does that answer your question?
Yeah. Thank you, Sanjeev. Thank you very much.
Yeah. So now, so we asked two questions. One is, what is the magnetic pattern of the spin subsystem, which is what we have answered so far with this effect, with the help of these effective Hamiltonians. And the other question is, how can the electronic properties be affected by such magnetic orders? Now so I'll just spend 2 more slides on this second question. And as I said earlier, that the answer to this question is easy, because once you have obtained the magnetic background, right, then it's essentially solving a 1-electron problem in that background, and that's this model, the Rashba double exchange model, is going to be the key to that, in the sense that you just set up this Hamiltonian for a given magnetic configuration and diagonalize this numerically, and then calculate whatever you want to calculate. And so here we have calculated Hall conductivity And we have calculated something called, which I'll not, will have time to go into detail about, the Bott index for the topological characterization and the local density of states. And a combination of these objects actually shows some very nice physics that that is contained in these systems. So let me just try to kind of focus on maybe one. So firstly, the Hall conductivity seems to be finite, and it has the same characteristic like a positive sign of sigma xy, and then across the half filling, then it becomes a negative sign, basically saying that this is the Hall. So electron-like physics here and hole-like physics here, and so on. Right? So now, if you look at the local density of states, which is basically measuring the overall density of states weighted by the presence of the electron in a certain region. So for a given wave function, you can ask whether there is a weight for that wave function at a site, and if there is a weight for that wave function at the site, that acts as a weight factor for the density of states. That's essentially the local density of states. And you can present the local density of states in two ways. One is you fix the energy omega, and then you plot the spatial pattern of these rho I omegas, or you fix the site I and then plot the energy dependence of the density of state. So here is the omega dependence at a fixed I, which actually shows this nice oscillation-like behavior. And here is a spatial dependence for a fixed omega. So in this picture, what is basically becoming clear is that, so this is the skyrmion state that we are using. And on this skyrmion state, we put the electronic Hamiltonian and diagonalize it. And if you ask, what do the electrons do in this skyrmion state? Well, the answer is this, that electrons like to bind to these skyrmions. So the electron density on the skyrmion sites are larger. So this actually, in the presence of electrons, this becomes a composite object, which each skyrmion is holding one electron. Well, not one electron, each skyrmion is holding certain density of electrons, preferentially over the other regions. So, and this is actually interesting. And to make it more clear, what we did is we constructed ideal looking skyrmion lattice textures. So by looking at our skyrmion textures, we sort of came up with this, and with the help of some published papers, we came up with a standard formula for the polar and azimuthal angle variations of spins for such skyrmions. And this formula fits our textures very well. Now, having understood these textures in terms of this closed form formula, what we can do is we can just place these textures on a lattice and make a nice periodic array of these objects. And now we solve the electronic problem in this background. And interestingly, what we find is Landau levels. So these density of states actually shows this periodic pattern behavior. And so there was no, so notice that there is no magnetic flux applied in the problem. These are only, so the presence of magnetic skyrmions is enough to generate Landau levels, and that's actually not that surprising in the end, in the sense that each object here is like essentially like a monopole. It's if you can define monopoles in 2D. So it's as if there is a fictitious source of magnetic field sitting somewhere here, and that fictitious source of magnetic field is generating for us the Landau level like behavior in the local density of states. And to confirm it even further, what we did is we take the Fermi level here, or take this omega right after the first Landau level, and ask what is the local density of states pattern in space, and that pattern is shown here. So the state this belonging to this Landau level lives on the edge. Then you can place the energy value after the second Landau level, and what you get is this picture. You have now two states living on the edge next to each other, and so on. So each of these Landau levels are going to be those states living next to the edge, and so on. So essentially, if the Landau level physics is emergent in such objects, and that is actually experimentally also seen, that skyrmion systems show this anomalous Hall effect, which means Hall effect without applying magnetic field and without having kind of magnetization in principle. and that is confirmed in our calculations as well. So that brings me to my summary, and hopefully there will be some time for questions. So just for the students, I want to kind of highlight the concepts that we touched upon in this talk. And in no way this is kind of a complete understanding of these concepts, but nevertheless, this is a good excuse for, you all to go back and just look up these ideas. So what we talked about is Hund's metals, Rashpa spin orbit coupling, magnetic fermions, RK-KY interactions, and double exchange mechanism. So I would suggest all of you to go back and familiarize yourself with these concepts more thoroughly. And in terms of the results that we presented, basically we try to attempt an understanding of fermion formation in metals using electronic Hamiltonians. And one of the key finding was that these filamentary structures, for which there was no clear understanding so far, have been explained as a sort of as an outcome of a degeneracy of some set of states, and they turn out to be the origin of the isolated.
Hello? Hello?
Your voice
That block.
is audible. Sanjeev, your voice is not audible.
He has lost the connection, I think. Vinod.
Let me contact.
I think he has lost the contact, probably. Vinod.
Yes, sir, I am contacting him. Just a minute.
Hello.
Yeah.
Yes, sir.
Okay. So since when I was not audible, this slide or last slide?
Just last. When you were summarizing.
Oh, last slide. Okay, all right. So I just kind of go back to my summary picture, I suppose, and we can come back to this in the question answer session. So yeah. So let me kind of repeat my summary. So what I said is that for students, we touched upon these key concepts, which students should try to look through or revise more thoroughly if you want to work in condensed matter physics or particularly this field. And in terms of new results, we tried to present a electronic Hamiltonian based understanding of fermion formation, and particularly the result about the filaments and the formation of isolated fermions by applying magnetic field on this filamentary state was one of the main results. And the other interesting result was this presence of emergence of Landau levels in terms of edge states and so on. And for more details on the recent work of ours, one can follow these papers. And thank you all for your attention.
Thank you, Dr. Sanjeev, for a nice, informative, and excellent talk. Now the presentation is open for questions. Yes.
Hello. Can I ask a simple question? Is there any specific heat for this system?
Specific heat data for this system should be available.
That will tell about what is your fermion heat.
Yes, sir. In fermion, there are a lot of data on heat capacity measurement.
So that should tell our fermion is a quasi particle type.
That okay.
Because you did with temperature also. You did some calculation with temperature. Hello.
Right. So we can compute.
You can look at
well, and
because you did and you did the structure factors. You can do time evolution. You can do of something.
Yeah,
Basically.
Any other question from the participant side?
That's right.
Yeah, Sanjeev.
Yeah.
Hello, Sanjeev, can you hear me? Hello. Hello.
Yes.
Yeah, Sanjeev. So I would like to ask the question regarding the possibility of quantum phase transition
Hello.
in your system. Yeah, can you hear me?
Yes, I can hear you.
Hello.
Not communication.
Sanjeev, can you hear me? I think he lost the signal again. Okay, I will type my question in the chat, and maybe Vinod can coordinate.
Yes, let me. I think there is some issue.
Well, everything went well
Hello.
so far.
Yes. Okay. Hello.
Hello.
Now you're.
I'm
now,
back. I
now.
think. Yeah. Right.
Okay.
Navinder, I could hear you, but you could. Yeah. Navinder, please go ahead and ask the question. Yeah.
Right. So my question is related to the possibility of quantum phase transition. So in you have explained when there is a fixed alpha and you lower the temperature, and then there is a threshold alpha and you get these fermions.
Right.
Now let us say that we do the calculation at zero temperature, at a zero temperature, and then very alpha. So whether there is a critical alpha where you can get this possibility of fermions, and then you can have a quantum phase transition.
Yeah, so that's right. So that's a very interesting question. So the point is so at least let me put it from our calculations point of view first. So in our calculations, these phases are seen as essentially classical phases, because see, we are looking at we are looking at degrees of freedom which are of two types: classical spins and electrons. And finally, the classical spin Hamiltonian is derived by integrating out electrons. So what we are left with is essentially classical spin system, and therefore there is no chance of a quantum phase transition unless one treats that model quantum mechanically. So that is an open question. If one treats that model quantum mechanically, that is actually possible to have a quantum phase transition.
But we can define some order parameter, right? So the order parameter is something which is not nothing to do with the classical or quantum. So there is an order parameter in the system. So there is a breaking, and below the critical temperature and a particular alpha, you get this order phase transition. So there is a possibility. I don't know whether it will be only calculation can tell that at zero temperature there is a critical alpha. Below alpha we have a order parameter. Above alpha we don't have the order parameter. So then this quantum phase transition can be put into of the form of the Landau-Wilson category.
I see. So if one defines well, I think probably it is not quite correct to call it a quantum phase transition, because if there are no quantum fluctuations available in the system, in the sense that if it's a purely classical system, then you're going from a classical ordered state to another classical ordered state. That is possible.
See the alpha is the strength of this Rashba coupling, right?
Yeah, right.
It's a purely quantum object. I mean, the Rashba coupling is driven by quantum mechanics. It's a fully quantum concept. It has no classical. So the point is that once the alpha becomes strong enough, so even at a zero temperature, you may get fermions. Even at a zero temperature, it's my guess actually. I don't know. One has to do the calculation. Because
probably you are right that one will get fermions.
Let's not call it a quantum phase transition. But let's say zero temperature. Once the alpha is increased, I mean the Rashba coupling is increased, so there is a possibility of phase transition. So some phase transition at zero temperature.
That is true actually. Yes. Absolutely. That is possible, but one needs to do. I think one needs to do calculations which are beyond what we did for that.
Okay.
Yeah. So we cannot answer that question within our calculations, where we kind of integrated out the electrons, and then. So although we started from a quantum model, but at some level the question we were asking was what is the magnetization pattern emerging, and that question could be addressed completely at classical level. Therefore, and
That's
within that limitation, we cannot answer this question. But yeah, this is a valid question and can be tried on a quantum mechanical treatment of this model.
Yeah, so you have to do
Yes,
the quantum
absolutely.
mechanical.
Absolutely.
Okay, okay.
Any other question? So if no more question, let us thank Dr. Sanjeev for such an excellent talk today. And I request Sanjeev and Dr. Pathak, Dr. Navinder, and all the faculties to be with us for a couple of minutes for the closing ceremony. Okay.
Sure,
So,
I'll be happy to.
okay. Yeah. Yes, Sarabjot.
Yes, sir. I'm here.
Yeah.
Yeah. Should I start?
Yes.
With valedictory? Okay. Okay. Thank you. Physics is really nothing more than a search for ultimate simplicity. But so far, all we have is a kind of elegant messiness. A warm evening to one and all. Reverend Guest of Honor, Professor K.N. Pathak, distinguished dignitaries, Honorable Head of the Physics Department, NITJ, Dr. Haleen Daya, worthy faculty members, and all the inquisitive minds who have joined us from far and wide. I, Sarabjot, welcome you all for the valedictory session of 5-day ESTC on current trends in condensed matter physics 2020 under the able guidance of Dr. Vinod Ashokan and Dr. Shishram Rewari. I promise this will be the last of the grilling sessions you heard over the 5-day journey, and not at all grilling one. Condensed matter physics is a rhythmic prose, elegant gymnastics for the mind, mirror of the creation, and the sole key to man's dominion over the planet. True to its importance, this STC witnessed an overwhelming participation. Thanks to internet and online apps too, we were all saved from paying for travel and meals. Time flies, and here we are at the end of our knowledge sharing days. I now invite Dr. Vinod Ashokan, Assistant Professor and also the course coordinator, to highlight the milestones of the course. Sir, please.
Yeah. Thank you, Sarabjot. So let me summarize the last 5-day activity which we did in short-term course. So we have generated a wealth of information and experiences by very eminent speakers in this short-term course. So on day first, 25th September, during the inaugural function, it is inaugurated by Professor L. Kevasi, Director, NIT Jalandhar, and welcome Honorable Chief Guest, Professor T.V. Ramakrishnan. He encouraged the participants and organizers for attending and conducting the short-term course. So, and further, the participants were welcomed by Dr. Haleen Daya, head of the department, physics department. And I also mentioned the objective and motivation for organizing this short-term course. This course has received a very overwhelming response. There were 763 participants, including faculties, postdoc, PhD, and master's students from various leading academic and research institutes across the India and abroad. We registered for this course. So in this course, we had 10 eminent speakers from some esteemed Indian research and academic institute participated as a resource person by delivering expert talk. So in the first session of first day, it was delivered by Professor T.V. Ramakrishnan, a Padam Shri, a Fellow of Royal Society, a Distinguished Associate of Indian Institute of Science, Bangalore. In a keynote address, he motivated the student by introducing the basics of theoretical condensed matter physics. With a special emphasis on the importance of the field, he delivered a talk on metals with a strong electronic correlation, in which he summarized present working picture of metals, mentioned some properties of strongly electron correlated metals. He then discussed some theoretical attempt at making sense of their properties with some characteristics application. And the evening session, Dr. Navinder Singh, Physical Research Laboratory, Ahmedabad, delivered a talk on an introduction to conventional and unconventional superconductivity, in which he shared some background to weakly and strongly correlated system, then introduces to the conventional superconductivity, which includes detailed discussions on BCF theory of superconductivity, a key highlight of his talk was the field of superconductivity. Then he discussed the material and electronic structure and problem of unconventional superconductivity. He summarizes the leading theories for the mechanism of unconventional superconductivity with some experimental facts. Among them, the Hubbard model for strongly correlated system, Anderson model, and related development, especially about cuprates and high transition temperature superconductivity. He also discussed the idea of Cohn-Littinger cluster extension of BMFP. He addressed the present status of the current theories of unconventional superconductivity and presented some of their investigation. On second day, the talk was given by Professor R.K. Modgil, Kurukshetra University, Kurukshetra. He got a talk on quantitative assessment of exchange correlation via Coulomb drag in electron-electron and electron-hole bilayer, in which he shared a light on the effect of many-body correlation, crucial role in determining the physical properties of the material. He discussed the Coulomb drag phenomena with recent experimental probe, physical realization of bilayer in 2D gas using gallium arsenic heterostructure. In his talk, he presented recent theoretical result obtained by his group on drag resistivity of electron-electron and electron-hole bilayer system by considering both the dynamic and temperature dependent of intra and interlayer correlation. The drag resistivity their group have calculated by considering the contribution from direct scattering processes using the semi-classical Boltzmann approach with a dynamical screen interlayer interaction determined within the framework of temperature-dependent dynamic self-consistent mean field approach of Singh. In the end, he demonstrated clearly the importance of including the dynamical nature of exchange correlation to have a reasonable amount of measured drag resistivity. On second day, the evening session, the talk was delivered by Professor Tulika Maitra from Indian Institute of Technology, Roorkee. She started her talk with a brief introduction to density functional theory and the various model parameters that can be derived from such calculation. She then discussed the recent calculation and results in 3 different classes of compound. The first one was the magnetically driven type 2 multiferroic, second geometrically frustrated magnetic material, third magnetic exchange driven type 2 Weyl semi-metal. So among them, the nature of spiral state and corresponding ferroelectric response in the incommensurate magnetic phase of type 2 multiferroic, the interesting interplay among magnetism, charge transport, and optical property in the layered triangular lattice antiferromagnet using density functional theory and Boltzmann transforms theory, and their DFT calculation were able to match and predict experimental observation were demonstrated. So in the third day session, the morning session, talk was delivered by Professor S.P. Das, Jawaharlal Nehru University, Delhi. He lectured on mechanics of many discrete and continuum description. He discussed how starting from simple laws of mechanics, we can understand the dynamics of many particles and develop a microscopic level model of physical phenomena observed in a macroscopic world. He explained such theories are important tool for explaining transformation between different phases of matter. He introduced states of matter, Brownian motion, correlation function, static and dynamic. He discussed continuum field theoretic model essential for understanding physics of many different scales, both spatial and temporal. It's used for understanding the role of conservation law and detailed balance in the equilibrium of a fluid consists of passive unit as well as units which are cell-driven or active. In the evening talk, Professor K.N. Pathak, Punjab University, Chandigarh, delivered a talk on metallic quantum wire. He explained the Gilliam model of a metallic electron gas and some of its properties, in addition to the behavior of electron in crystalline solid. Subsequently, he discussed the one-dimensional quantum Fermi gas with Coulomb interaction. He discussed the experimental realization of 1D system, the behavior of one-dimensional physics with momentum distribution and particle hole excitation picture. He discussed how to confine an electron gas in one dimension theoretically. Later, he presented some of his latest results, that is pair correlation function, structure factor, and momentum distribution of one-dimensional quantum electron wire. Obtained using quantum Monte Carlo method, he showed in the high density limit the structure factor and exchange energy or analytically obtain and exactly obtain. Further, he showed these are exact results obtained which perfectly agree with the quantum Monte Carlo simulation. Some aspects of Tamanagho-Luttinger behavior of one-dimensional electron gas is also discussed. On fourth day, the talk was delivered by Professor Sumati Rao, Harish Chand Research Institute, Allahabad, delivered a talk on topological phases of quantum matter. She chronologically introduced the development of the field of topological phases in the last 10-5-year development, and she gave an overview of the basic idea of this field, starting from the quantum Hall effect and then leading to topological insulator, topological superconductors, and Weyl semi-metal. She ends with a brief mention of the current frontier in the field. On fourth day, the evening session talk was delivered by Professor Vikram Tripathi, Tata Institute of Fundamental Research. He delivered a talk on spinon in magnetically ordered phase on MDL approach. He discussed various topics like quantum spin liquids, spinon in quantum spin liquids, magnon and spinon in two dimension. He introduced the Kitao model and throw light on the excitation, Kitao spin liquid, a deconfined phase, Kitao material, and realization of modeling Kitao material, and quantized thermal Hall in Kitao material. And and the fourth day, the fifth day, today's session, the first talk was delivered by Professor Sunita Srivastava, Punjab University, Chandigarh. She delivered a talk on properties of topological semi-metal, lanthanum monopexide. She summarizes the electronic structure topology of crystalline material, which emerged as a major new theme in the modern condensed matter physics in the last decade. She presented few results of her ongoing research work. First principle calculation have been carried out to study the structure, electronic and thermoelectric properties of LABI by making use of density functional theory, combining with semi-classical Boltzmann transport theory. In their recent work, they found the topological character of LABI is found to be in agreement with available theoretical and experimental study. And the last talk by Dr. Sanjeev Kumar, IISER Mohali, delivered talk on magnetic scramions in Rajba Kapil-Hun's metal. During his talk, he discussed magnetic scramions are topological stable texture that have been observed using a combination of microscopic techniques in thin films, a variety of magnetic metals. So these are being considered as a building block of next generation low power data storage and processing devices. This talk has provided a microscopic origin of these unusual magnetic structure. Yeah. Thank you.
Thank you, sir. I bow my head in gratitude to Professor K.N. Pathak, a former Vice Chancellor, NASI Platinum Jubilee Fellow, Professor Emeritus, Punjab University, Chandigarh, and Fellow of all three prestigious Science Academies of India for gracing the occasion as the guest of the honor. Sir, I request you to bless us with your inspiring words before we depart.
Thank you so much. Vinod has given a very good summary of entire picture of these 5 days activities, and I will say it has been really wonderful. He was able to invite topmost physicists of the country of national as well as international reputation. And the number of attendance which I have been seeing, even at the end of the lecture, there are 100 participants at this time on this platform, and there are many on the YouTube. So you can judge the success of this this program yourself. It has been really wonderful. There has been lecture of very high qualities. I would simply suggest that probably graduate students, senior graduate students, and postdoctoral, they might be able to understand quite a bit. But the beginning students, there might have been some problem with them. So I would suggest that the NIT Jalandhar should make it a point to organize the annual seminar every year. And further, I would suggest that it is not only in one field. They should combine all the fields which they are working. Because the Delhi University started in the early days, 60s, to organize the some visitors program, and that is how it became very famous, popular department of the physics. So, and they used to invite physicists of all branches. So I think this is time government is emphasizing to have interdisciplinary work. So they should organize seminar for 5 days in this format and having lecture from all the fields. So this is suggestion for them to consider. And with these small remarks, with these brief remarks, I will wish you all the best. And thank you for asking me to close this seminar. It has been wonderful. And thanks all the faculty member, Mrs. Dahiya and director for providing this opportunity. I think this method of our organization doesn't cost much money. So they can afford to do it, I think, every year. And Vinod has done really very hard work, I think. So we should give cheers to him. Yes. Thank you.
Thank you, sir. Thank you. Thank you. And your point has been noted.
Thank you, sir, for your motivation, and I'm sure we'll put into reality your kind suggestions. We make a living by what we get, but we make a life by what we give. I once again invite Dr. Ashokan to present a formal vote of thanks in absence of Dr. Shishram Bebari, the other course coordinator, who could not be with us
Excuse me, ma'am.
due to some official engagement, but definitely has a heart full of gratitude. Yes, someone, Mohammed Shaukat, sir.
Yes,
Yes.
ma'am. Can you please send me the feedback link?
Yeah, I can have something, I think. That's
Yes,
very good.
yes. We'll
Very good.
send you that shortly, and it will be put in this chat section after we depart.
Okay, ma'am.
Sir, please.
Okay. Thank you, Sarabjot. Honorable Director, Sir, Professor L.K. Avassi, he was engaged with some other meeting today. Guest of honor, Professor K.N. Pathak, Head, Dr. Haleen Dahiya, faculty members, and great speaker from various prestigious institutes, and all dear participants. I'm feeling privileged to extend vote of thanks on this occasion. I believe this 5-day course must have increased your entropy and in a sense expose you to several areas of ongoing research in theoretical condensed matter physics. So on behalf of Department of Physics, I would like to extend my sincere thanks to the Honorable Director, Professor L.K. Avasthi, for his constant support for various activities at NIT Jalandhar. The short-term course is another example of his dedicated effort. A special thanks to TQ3 to sponsor this STC. Thanks to chief guest of the event, Professor T.V. Ramakrishnan, IISc Bangalore. A lot of thanks to Professor K.N. Pathak, sir, for his constant monitoring in this STC and to guide us. Since we are new in these type of activity, so your presence in all the lectures gave us confidence and support. Thank you, Professor Pathak. All the speakers have managed to present their talks so well on the e-platform. Your patience to manage all the audio, video issues in the session need to be appreciated. Thank to Dr. Harleen Dhaya, head of the department physics. She is a constant support for physics department always. Thanks to all the participants for their cooperation in management of this short-term course. Being a member of organizing team, I have seen the effort of Dr. Shishram. This STC has been successful due to all his management skill. It was really good experience to work with you, sir. And I hope we will work together in future also. Thanks to our PhD student, Mr. Ankush, Sarabjot Kaur, Mayur, Rajesh, and all the members of Physical Science Society for their constant support in this short-term course. Thank you. Thank you, all the participants who made this event successful by attending each and every session. Thank you once again. Thank you. Thank you all.
Thank you, sir. As a concluding remark, I would like to add, the important thing is not to stop questioning. Curiosity has its own reason for existence. One cannot help but be in awe when he contemplates the mystery of eternity, of life, of marvelous structure of reality. It is enough if one tries merely to comprehend a little of this mystery each day. As Albert Einstein says, Never lose a holy curiosity. I request all the participants to fill the feedback form. Thank you, one and all. Stay safe and healthy. Here is Sarabjot signing off till we meet again. Thank you.
Thank you. Thank you, everybody. Thank you.